So let's summarize what we've learned today. So we started by talking about the Lorentz group, which is the set of metric preserving transformations. That is, if we want to preserve the space-time metric or space-time interval or space-time measure, we saw that it was useful to define this quantity G, which was this matrix, with zeros everywhere else. Okay, and the set of transformations lambda such that lambda transpose G dot lambda is G defines a group of matrices, and this group is called the Lorentz group. Okay, and this group consists of the operations of boosts, rotations, which are continuous transformations, and the discrete operations of parity and time reversal. And another important property of this group is that it's a non-abelian group. Okay, we didn't discuss this earlier in the lecture, but boosts in general do not commute with each other, and they do not commute with rotations. The order in which you do these operations matters. And similarly, rotations do not commute with each other. Okay, so this is what is called a non-abelian group. And we saw that while it seemed like overkill to define the set of operations just for the space-time 4-vector, we saw that there is a generalized notion of 4 vectors, which many quantities obey. So we saw that not only is there a space-time 4-vector, there's also a velocity 4-vector, there's also a partial derivative 4-vector, and these quantities all transform in the same way. That is, if I want to find out what they are in the primed coordinates, I would just calculate something like this, where this is matrix product lambda dot x, u prime would be lambda dot u, and partial prime would be lambda dot partial. So we came up with this generalized notion of 4 vectors, and this generalized notion of 4 vectors is an obvious generalization of 3 vectors. So 3 vectors are objects where if I want to construct an object A prime in a rotated reference coordinate system, I would apply a rotation matrix, which is a 3 by 3 matrix, to A, which is a 3 vector. So if I have 3 vectors, I rotate by a rotation matrix, and that would give me my new 3 vector in my rotated coordinate system. So similarly, 4 vectors here involve transformations not just in space, but in time as well. The transformations in time are interpreted as Lorentz boosts. That is, you're going to a frame which is moving with respect to the frame that you started with. And the power of identifying 4 vectors is that the transformation laws become universal for all 4 vectors. All 4 vectors transform in exactly the same way. Okay, so we don't have to worry about the complicated rules for the transformation of ux, uy, and uz. If we correctly identify the 4-vector combination, the 4-vector combination transforms in a very simple way. Okay, so it'll be useful to identify what objects are 4 vectors, and then we just know the transformation rule. Once we know this transformation rule, it's simple to then derive the rule for transformation of ux, uy, and uz if we need to. Okay. And the last thing that we saw is the idea of Lorentz scalars, which are dot products of 4 vectors. So we defined a generalized notion of a dot product So this dot product was defined as, if we have a 4-vector V and another 4-vector V prime, the dot product was defined as V transpose dot G dot V prime, where this was a matrix product. Now, if you compare this with what we know about 3 vectors, so for 3 vectors, if we write down a dot product of 2 3 vectors, conventionally, if we think of A as the 3-vector AX, AY, AZ, and B as the column vector BX, BY, BZ, then we would say that this dot product is a scalar quantity under rotations. It doesn't transform under rotations. It's AX, BX plus AY, BY plus AZ, BZ. In matrix notation, we write this as A transpose dot B, okay, where dot is again matrix product. But you see that secretly, you can think of this as having a metric in here. So I can write this as A transpose dot identity 3 by 3 dot B. So if I look at only the subset of 3 by 3 transformations, okay, within these 4 vectors, since the metric G in its diagonal components has the same sign for the lower 3 by 3 entries, okay, the dot product, if I only look at the, if I ignore the time component, or if the time component is 0 for these vectors V and V prime, I would exactly recover the dot product of 3 vectors, okay. The difference between 4-vector dot product and 3-vector dot products is not just going from 3 dimensions to 4 dimensions, but also the fact that the metric is different. It's not all the same signs. The time coordinate has a different sign in the metric. The time-like coordinate has a different sign in the metric than the spatial coordinates. Okay, so this is the generalized notion of 4-vector dot product. And we've seen that just as 3-vector dot products are invariant under rotations, so 3-vector dot products are invariant, that is, they do not change under rotations. 4-vector dot products are invariant under Lorentz transformations. Okay, and this includes rotations and boosts. So in the next class, what we'll do is we'll see that there are more general objects which transform again in very simple ways, but are different from the but have different transformation rules than that of 4 vectors and these Lorentz scalars, okay, which do not transform. So these generalized objects are called tensors, and they are a generalization of tensors that we have seen maybe in a classical mechanics course in 3 dimensions. Okay, so the moment of inertia tensor, for example, is one such tensor. And it has a well-defined transformation law under rotations. We will see that there is a generalization of this idea of transformations under Lorentz transformations to define objects which are called tensors in 4 dimensions.